Okay, so good morning, everyone. Thank you for coming to an early session. You are all super enthusiasts for these technologies, so are we, and we've got a lot to talk about today. To be honest, we're probably going to breeze through some of the slides. They're going to be available for you to peruse and click all the links. You don't have to take, hurried notes or anything like that. Just enjoy, watch the demos that we have. Ask plenty of questions. Again, we're going to try to leave plenty of time at the end for that. And the way that we're going to get there is by not doing some of the slides. Okay, so let's get started. So my name's Ken. I chair the WebGL working group at Khronos. Today here are Kai Ninomiya, who is the WebGPU spec co-editor, and Stephen White, a longtime graphics expert on the Chrome team, and he's got some really cool combined languages to show you today. So photography is welcome, but you don't have to take pictures of the slides. They're all going to be posted. So again, please just enjoy. So here's the agenda. We actually have a pre-recorded presentation from a gentleman, Pawel Misiurski, who couldn't be here today. He's in Spain enjoying life, but he did make an awesome presentation and pre-recorded, so we'll play that later. So brief WebGL update. Khronos is fully supporting WebGPU development at the W3C and WebGL development within Khronos. We are all working for a smooth transition between the APIs. And as you know, WebGPU finally brings compute shaders to the web portably. This is a fantastic advance, and a lot of cool stuff has already been built with it. However, WebGL is everywhere, and it's going to be here for years. It's not going anywhere, so you can still deploy your WebGL applications with full confidence and know that it's going to be supported in all web browsers forever, basically. So we are continuing maintenance and evolution of the ecosystem. Work is still ongoing in Engel's Metal backend for macOS and iOS, fixing bugs, making it more performant in certain corner cases. Firefox is actually considering switching to Engel Metal on macOS, and I realized that I missed something. We have a new working group representative from Mozilla, Ashley Hale, and want to thank publicly once again Kelsey Gilbert for many, many years of service on the WebGL working group. Actually, maybe we could just give Kelsey a virtual. Okay, so now Firefox is actually considering switching over to Engel Metal because their WebGL implementation is still hosted on Apple's OpenGL driver, and it's not supported anymore, I think, as we all know. So in Chrome, we are continuing work to use Engel everywhere for the WebGL implementation. This is to get feature parity across platforms and fix really old bugs. There's been more recent performance work on Android, which is the last holdout platform to try to get the thing shipped there. The Pixel Local Storage extension that Chris Dalton from Rive has been championing is progressing. It's unblocked now. There's agreement on from all the browser vendors on the form of the extension, so we've done some recent cleanups and refactors. There's a couple more fixes, and then it's going to be ready to ship. And there's also consensus among the browser vendors to finally ship the base vertex and base instance extensions, and so after a couple more bug fixes, those will be ready to ship too. But now I want to talk to you about something that I teased at the Fast Forward, and a project that I'm personally very excited about, which is called WebGL and WebGPU. So this project was initiated by Jeff Lang, Engel's tech lead, and Corentin Vallet, the WebGPU tech lead, and Chrome's security team, and you'll see why. So Engel is widely used as the native WebGL implementation in browsers, and it's got backends to multiple graphics APIs like Direct3D11, Vulkan, Metal, and even OpenGL and OpenGLES. It virtualizes the OpenGLES API on top of even OpenGL. It uses one hardware context and gives the appearance of multiple contexts and does its own state caching and state switching internally. Okay, and that's how it is able to be implemented on radically different APIs, such as, say, Vulkan. So what if Engel had a backend to the WebGPU native implementation? Okay, so this is what the inter-process communication protocols look like in Chrome for WebGL and WebGPU. And this isn't the whole story, but I'm not an expert in Google Slides, and I couldn't cram more text in various places here. So in the JavaScript or renderer process on the left, you've got the WebGL implementation, and it's remoted to the GPU process via something called the GLES2 command decoder. On the JavaScript process side, it actually looks like OpenGLES, okay? But it's a remoted implementation of OpenGLES. In the WebGPU case, it's a totally different communications protocol, okay? It's the Dawn wire. Dawn is Chrome's native WebGPU implementation. And in the JavaScript process side, you've got the Dawn wire client, okay, which looks just like the native Dawn API, but again, it's remoted. So right now, there's two different ways that the JavaScript process talks to the GPU process. And this is done for sandboxing reasons. The GPU process doesn't run any end user code. I mean, shaders, but even those are validated and translated. So these are some details of what's going on. See, Angle vectors off into various low-level APIs, and so does Dawn. So what if Angle talked directly to Dawn? Okay, I mean, Dawn is an implementation of a little bit more abstract, but still low-level and explicit API, kind of like Vulkan. Well, in that case, you can basically take the Dawn part of that, and you can recompile the whole thing and have Angle talking to the Dawn wire client too, okay, just like the WebGPU implementation does over here. And then you can take Angle and move it out of the GPU process and move it over into the JavaScript process. All right, and the JavaScript process is heavily sandboxed. All right, this is totally untrusted code, and it's done this way so that to protect users from anybody who tries to to hack somebody's computer, basically take advantage of a bug that may ultimately turn out to be a security bug. And at that point, you've got exactly one communication protocol between JavaScript and the GPU process, and that's the Dawn wire protocol. So there are plenty of advantages for doing this, and I actually forgot to list a couple of them, but for one, Angle receives an automatic upgrade to D3D12. We never built that backend, but since Dawn uses it, it would automatically start using it. It will be using the simpler and more efficient Dawn wire protocol, which is a modern rethink of exactly how signaling happens between those two processes. It will dramatically reduce the amount of trusted code inside Chrome's GPU process. That's really the key. It's hundreds of thousands of lines of code. Every line of code nowadays is a liability, as we all know, right? With security researchers fuzzing everything everywhere all at once. And this will make the entire system more robust. And among other things, it'll reduce cross-platform differences. It'll basically make everything behave much more similarly between platforms. And it'll rehost Angle's shader translator on top of a more robust WebGPU shader compiler stack, which can do much better transformations than the old GL slang shader compiler that's currently in Angle, and we'll get more correct WebGL shaders. Like the ternary operator will finally work correctly on the HLSL backend. So plenty of advantages for this project. Now, a couple of challenges is that it's going to be difficult to match the performance of Angle's like hand-tuned backends, which have been in development for over a decade and have really been tuned. And also, in order to get feature parity, we'd require many WebGL extensions to be supported. And that is going to be tough, and I don't have a solution for you right now, but we'll keep working on it. You can please follow along on this bug. You don't have to write it down in a hurry. You'll have these slides in a little while, and you can just click it, and the dependent bugs that are filed off of it. So anyway, that's the exciting news on the WebGL side. Now I'd like to please hand off to Kai for the WebGPU updates.
Thank you, Ken. Hey everyone, I'm Kai. I work on Chrome, and I'm also one of the editors for the WebGPU specification. And I will be giving an update on WebGPU. By the way, I didn't tell Ken this, but that link on the slide in the top corner takes you directly to the slides. I have a bunch of links in my slides that don't have URLs, so go there and then click the link. So just a super quick intro for people who aren't super familiar with WebGPU. It's a modern graphics API for the web, a successor to WebGL. It's easier to use, less stateful. It gets us things like compute shaders, but it's also a foundation for a lot of future features like bindless resources, ray tracing, multi-threading, all sorts of things that we really would like to see on the web. Standardization happens on GitHub and at the W3C, so everything is in the open and anyone can join and participate in the development, so we encourage you to join. I also want to talk about WebGPU compatibility mode. So this is a really important effort that we're working on right now. This is basically WebGPU on OpenGL ES 3.1. So compatibility mode, we estimate, as far as its hardware requirement, will run on about 90% of the machines, more than 90% of the machines that WebGL 2 currently runs on. So that's a pretty decent chunk of market share today, and of course will increase over time. But it has compute shaders, right? So this requires OpenGL ES 3.1, and we get the compute shader support from there. It is forward compatible, so it's very easy to upgrade to full WebGPU. Basically, if you just don't turn on compat, then your application will still work. And there is a laundry list of limitations. A few things that you might actually run into in porting, but most of these things you're not going to actually encounter. So there's a couple of notes here about the most notable things. And I just want to call out Stephen, who's done a lot of work on compatibility mode, both on the implementation and on the specification, figuring out all these limitations that we need to be able to do this. And that will get us much better reach on, especially on older Android devices, potentially also on Chrome OS and maybe even Windows 7, if that ends up being important. We'll see. So the really important WebGPU updates are Firefox has shipped in Firefox 141 on Windows, so huge congrats to the Firefox team for that milestone. And other OSs will be coming soon. Safari also has WebGPU provisionally available in the OS beta, so it's on by default if you are using macOS 26 or iOS 26 beta. That doesn't necessarily mean that they will ship, but it does mean that they are confident enough in it that they feel that it could. So that is a really important milestone for them as well. If you are a developer and you want to you want to develop WebGPU content against Safari, you don't have to get the beta, you can just use Safari Technology Preview, and that will have the latest implementation. Unity, one of our key partners, reports that their WebGPU exports are working well in all of these browsers, and they exercise the API pretty well. So these implementations are in pretty good shape. There are a few gaps here and there, but they're very well-known things that will get filled in pretty quickly over time. On the Chrome side, our WebGPU shading language implementation switched to a new IR-based implementation for better compilation performance. And compatibility mode that I was just talking about is available in Origin trials. So that means that you can get a token from Chrome and use it in the wild. So early adopters of WebGPU compatibility mode can ship today, and you will be able to make sure that your application is running with compatibility mode restrictions on users' machines. There might be small changes, and there might be a gap before it ships for real, so don't assume once you get the Origin trial it's going to stay online, but you can start adopting it and trialing it. On the standardization side, compatibility mode, again, is making good progress. Standardization is well underway. Most of the changes to the spec have been approved. We're doing that development in a branch, so once everything is ready and the working group is ready to ship it, then it will all arrive in the main specification at once. On more updates on the standardization side, there are a few new features that are fully standardized, and they're available or in progress in Chrome at least. I don't know all of the implementation status for everything in all the browsers, but we have shader subgroup operations, a bunch of texture capabilities, HDR canvas output. There's a bunch of features that are currently in standardization. So we have texture views with Swizzle assignment, and Wigzil, which is a big porting pain that happens a lot with porting from GLSL and HLSL. Cooperative matrix multiplication, primitive ID, HDR input, bindless resources. So bindless resources is a really big one. This basically means that you don't have to figure out what you're binding to every draw call or every dispatch anymore. You can kind of just put all of your resources in one big bucket and have them accessible from the shader. This is a big feature. It's in pretty early design phase. It's difficult to make work on the web because of the web's security requirements. So please be patient, but this is something that we are actively working on and hoping to be able to standardize. And then there are a few other upcoming features that are not like currently being worked on, but so WebXR is available. WebXR integration is available behind a flag in Chrome, so please try it out and give feedback. Shader immediate data, so like push constants for feeding small bits of data into the shader, and lots of other things that we have on our roadmap to work on soon for standardization. And we do expect most likely a higher pace of standardization once Firefox and Safari have fully shipped, because those teams have been very heads down in getting those implementations out the door. Once their implementations are out and they've gotten everything working, then they'll have more time to work on standardization, and they'll have more time to work on new features and prototype and all that stuff. And there will be standardization progress regardless, because we have a face-to-face standardization meeting upcoming just next month. Next thing is WebGPU.h. So for those not familiar, this is a C API for WebGPU, analogous to OpenGL ES versus WebGL. And so the goal is to have multiple interchangeable implementations. Right now we have two that are compatible, but we want to have at least Dawn, which is Chromium's implementation, and WGPU native, which is the C bindings for Firefox's implementation, as well as WebAssembly bindings, so that you can use your C++ or whatever application against WebAssembly against the browser's version of the API. And the really key part of this for WASM development is that you can develop and debug on native and then ship on WASM, rather than having to do all your debugging in WASM, because the native debugging tools for graphics are much better. It'll be much easier to get your engine ported over to WebGPU in native. Here is sort of an overview of that ecosystem. So at the top we have the WebGPU standard, which defines a JavaScript API that's implemented by each browser. And each browser has a different implementation. So Dawn, in the case of Chrome and Firefox, Dawn and WGPU, which are written in C++ or Rust. And then native applications, like your native application, can also use these libraries, Dawn or WGPU, to use WebGPU in a native application. And then now that you're using that API, you can retarget against WebAssembly, and you'll use the bindings, either the Emscripten bindings for the C API or the Rust bindings for the Rust API, and that will go back down to the JavaScript API, and you can run it on the web. Updates on WebGPU, so .h, the header is now stable, so that's the core part that's defined in the upstream repository. There are also extensions in the implementations, but that core part is now header stable. So use your implementations WebGPU.h so that you get those extensions and if there are any small differences, so that you're compiling against the correct one. Behavior might vary, so the header is stable, but the behavior might vary a little bit between implementations as we fix bugs and compatibility issues. So please report any compatibility issues that you find between the implementations. The current status of implementations is Dawn and MDawn WebGPU, which is the bindings for Emscripten, implement the stable core API. MDawn WebGPU recently had all the known show-stopping bugs fixed. It is working pretty well, but it is not super well tested, so we know that there are probably going to be more bugs. But it is working well enough that we have deprecated and we are removing Emscripten's built-in WebGPU bindings, which use an old version of the header. And we're about to remove those in favor of this other flag, which will just use MDawn WebGPU. WGPU native works, but the header has changed since their implementation was last updated, and it is not currently being worked on. So if WGPU native is something that you are interested in using, then we highly encourage contributing. It needs contributions. They are not probably massively complicated, but there are some major changes to the header, including how we deal with asynchronous operations. All right, so there are lots of cool things on WebGPU. These are all 3GS based. You can check these out. If you have a browser and device that supports WebGPU, then you can just go to the slides and click the link. I'm not going to show any of these, although they are all very, very, very nice. I will show one quick demo from our friend and coworker, former coworker Arman. He wasn't able to present this himself, but let me switch over to the demo. Come on, there we go. Okay, so It is a path tracer. And here we have a standard Cornell box with a nice area light. Hopefully, yeah, it's a little bit dark on the slides, but I think it's okay. We can add some sun lighting. And you can see that it updates live as we're looking at it. So it renders and converges quite quickly. And then we can move the light around to get some nice sort of evening lighting, some nice indirect lighting. So here we can get a good contribution from the scattering from this red wall into the scene. Still converges pretty well. This is all, of course, accelerated in WebGPU. So we can look at the bounding volume hierarchy for the scene. And this is showing the BVH that the application constructs. So this application is running in WebAssembly. The BVH is in software. It's compiled by the application and traversed in a compute shader. So the path tracing is happening inside of a compute shader, and it traverses this BVH from data that it pulls in from main memory. There's a few other very nice scenes here. So we can see a bunch of different rendering features. Let me just do this. Sorry, a little bit difficult to drag this. Okay, there we go. Bring the sun down really low. We can see some really nice scattering against the ground, some really beautiful effects, and you can also see it converges very well for some of these effects, and for others there's the typical fireflies. You can also turn like importance sampling on and off, and so you'll see that it converges much more slowly if you're not using importance sampling. So a really nice demo where you can see a lot of techniques. And yeah, there's a whole bunch of scenes here where you can see different materials. These are mostly test scenes, but some good different material properties, depth of field, some very challenging scenes with indirect lighting and all this. So this is a very cool demo. Check it out. This is all running on this laptop. This is an M1 or an M3 MacBook. Runs super well, no problem. This is I'm running it basically full resolution, and it's running super well, and it converges very well. So this is a really cool demo. Just wanted to show that, and then yeah. So I'll hand it off in a second, but thanks to Khronos for hosting WebGPU as always at the WebGL WebGPU BOF. There is a long history of cooperation between Khronos and W3C, especially on WebGPU and WebXR, which are W3C standards, but also exist in the graphics space, and so are very important to Khronos. There's a bunch of links here, so resources, learning materials, samples, demos, developer tools, libraries, and of course engines that have WebGPU exports. So all of these resources you can find on the slides. So take down that link, or you can find it later on the schedule for the Khronos BOFs. Please join the WebGL and WebGPU communities. We have vibrant online communities, and if you're developing with these APIs, we would like to hear your feedback, your input. On the WebGL side, we have a couple of mailing lists, so please join WebGL dev list. We have a chat room on the Matrix platform where you can talk with browser implementers and other developers. And of course, you can find cool stuff on social media. On the WebGPU side, as I said earlier, our development is all done in the open on GitHub, so you can find the main repository and report issues with the specification, talk about upcoming features, etc. We also have a chat room. Browser implementers and developers are there. It's pretty active. There's posts every day. And of course, you can also find things on social media. So we look forward to hearing from you. So thanks again to Khronos, and thanks to all of our partners, adopters, experimenters who have been doing various levels of things with WebGPU and have made it what it is today. And with that, I will hand it over to Stephen.
Thanks. Excuse me. Thanks, Kai. Those are some awesome path tracing demos, I have to say. I'm Stephen. I'm here to talk to you about a project called Toucan, which I call a language for graphics. So first up, some disclaimers. This is not an official Google project. It is a passion project of my own. It's not up for standardization, but you can think of it as middleware, so standardization is not really required to run it on the web. And it's not complete, so syntax and functionality may change. So, first up, what's with the name? Well, toucans are colorful, interesting, and fun, and I hope that the things that people could create with this tool would also be colorful, interesting, and fun. This is my second choice. This is a state fish of Hawaii. It's beautiful, but its name is Humu Humu Nuku Nuku Apua'a, and I thought people might get annoyed if they had to type that every time they wanted to compile something. So, a new language, huh? I often hear that's a hard sell. Believe me, I know, I live in Quebec. I'm very aware of the dangers of suggesting to someone they use a different language than the one they're familiar with. That said, I will try to make the case. Let's go back. So here's my case. And first of all, this is not a diss against any of the existing APIs. I feel this is a problem that just can't be solved with the shading language or API alone. But before I talk about the GPU, I'm actually going to talk about the CPU, which is where this project started. SIMD on the CPU is an alphabet soup of SSE, Neon, AVX512, and so on. And the libraries and programming models are all different. Excuse me. I wanted to provide the same graphics-oriented toolkit to the CPU that shaders provide to the GPU. Before you fall into a deep acronym-induced slumber, let's do a quick demo. I hope this works. If I click it here, nope. Maybe if I click it here. Demo gods are not happy with me today. Oh, there we are. Okay. This is actually a skybox I shot in the river behind my house. Well, not actually in the river, but. So I used that as a reflection map, and I put a shiny teapot in it because I have strange hobbies. This is the classic Utah teapot rendered from the original bicubic surface patches, animated on the CPU and tessellated on the GPU using a compute shader. Oops. How do I get back to the slides? I don't know what I've done. Come in. Ah. Okay, I'm going to get rid of this tab and then. Okay, I think we're good. Right. So it shows off one of the advantages of Toucan. Here's some Toucan code. It's shared code. So this is a cubic spline segment represented as a class in Toucan. It's templated on the control point type. It's instantiated on the CPU as a 1D float to do an ease in, ease out timing curve, and instantiated on the GPU as a float 3, representing control points of the tensor product spline patches. As new features like templates are added to Toucan, they're available in both the host and the device. So that's cute, but what else can we do with a common language? Well, you could use it for debugging. You could write a function or template on the CPU, debug it with your favorite CPU debugger, and run it on the GPU once it's bug-free. That's actually how I developed the teapot tessellation. But thinking bigger, it could also allow us to think more holistically about the graphics system. Rather than the strange bedfellows of two heterogeneous processors, perhaps we could unify them. One of the things that bugs me about the graphics APIs is that the left hand doesn't know what the right hand is doing. For example, that nicely structured storage buffer data that you declared in your shader, it's still just a big bag of bytes as far as the CPU is concerned, transferred as a void star. Types, offsets, alignment constraints, those are all up to you to get right, and if you get it wrong, the result is usually a black screen, never an error message. Vertex layouts have to be declared on both the host and device with different syntaxes for each. Similarly for storage buffers, bind groups, and pipelines. In my opinion, it's double declaration hell. Bindings use group number and binding numbers across the divide, which is dumb because you've already declared them and given them meaningful names on the shader side. So here's how you declare uniform buffers in Toucan. You declare them once, uniform is just a class, and then you write to them on the host with the same syntax and data types that you use on the GPU. And you might use the same matrix, multiply, and all the other math operators are available in both. Here's how you allocate a uniform buffer in Toucan. You might recognize the uniform keyword from shader code, but it's now also available on the host side, which means it's part of the type. Buffers are also templated on the type of data they hold, in this case, the myUniforms class we declared earlier. The device-side binding point is simply the type of this variable. Oops, sorry, I keep expecting the, anyway. A pointer to uniform buffer of my uniforms. Because the usage and contents are part of the type, usage errors can be caught at compile time rather than runtime, and the buffer contents errors can be caught at compile time rather than not caught at all. Another interesting point, you'll see there's no actual size parameter passed here. The buffer constructor does have a second parameter, which is the size, but it's a length, and it's in terms of the template argument. So it's like defaults to 1, meaning 1 of my uniforms. This leads to a kind of interesting design decision I stumbled into, which is to not have a size-of operator at all in the language. Why should we care? Excuse me. Why should we care about byte sizes and offsets when what we really care about are pixels, vertices, and user-defined data structures? So those should be our units, not bytes. Looking quickly at vertex layouts, it's quite similar. We declare our vertex class. We stack allocate a host-side array of that class, create a buffer templated on that same type, initialize it with the same syntax and data types that we then read from in the shader. One interesting use case for modern GPUs is combining compute and rasterization. For example, writing a vertex buffer in a compute shader and then reading from it in the vertex shader. Type qualifiers solve that multi-use buffer problem in a kind of elegant way. We just add a new qualifier. I'm kind of old-fashioned. I believe programming languages should, to some degree, read like spoken languages. Here we're allocating a new vertex storage buffer of my vertex, and that's what I do, new vertex storage buffer of my vertex. You'll notice that the array syntax is actually kind of like Golang. I stole it from because all the cool kids seem to be doing that now. I was convinced by a coworker that reversing the types is actually a really good thing, and I have become convinced. Right. So in this case, we have a runtime-sized array. So we actually do have an explicit length parameter of 3, but that length is in vertices, not in bytes. When you're assigning to the binding points, essentially having these qualifiers ensures that you're matching up the binding. And if you omit one of those qualifiers, the binding just won't work. It'll be caught at compile time. So here's a simple demo of multi-use buffers. It's a physics demo with springs and masses and Hooke's law. So this is running in the compute shader. I do have another version where I ran it on the host side as well to debug it. And the resulting positions are drawn in the vertex shader. So zooming out a little bit, what does a pipeline look like in Toucan? Well, just like buffers and vertex layouts, a pipeline is just a class. The shader entry points, the vertex and fragment shaders, are member functions of that class. And the member variables can be one of 5 things: vertex inputs, index buffers, color outputs, depth stencil outputs, and bind groups. So it's kind of like a declarative form for pipelines. How do we use it? Well, first we instantiate a device-side render pipeline templated on the myPipeline class that we declared earlier. This introspects the class, extracts the shaders and the pipeline variables into the internal layout structures that the graphics APIs require. Render pass, which is really like a render pass encoder from WebGPU, is also templated on the type of pipelines that we'll draw. So just as we did with the buffer, we stack allocate an instance of the pipeline class, assign to its members, then construct a render pass from it, and then we can set the vertex buffer and bind group and draw. Oops, there's the draw. So in this way, Toucan replaces all of the individual render pass calls and other APIs with a single call, set, taking an argument of the user-defined pipeline class. It removes the footguns of slots and indices and makes all assignments type-safe and by name. However, because we have list initializers in Toucan, we can do better. We can allocate the host-side pipeline instances implicitly. Here we use one in the render pass constructor to set the color output, and one in the set call to set the vertices and bindings. So this realizes kind of my simple dream, which is that assignments to pipeline variables should actually look like assignments. They're type-safe and by name. This is like designated initializers in C++. putting it all together, this is Hello Triangle in Toucan. It's 21 lines. My goal was to get it down to 20. I've not gotten there, but I'm stubborn and I'm convinced I'll get to it. Unlike other Hello Triangles, it doesn't hard code the vertices in the vertex shader because I think that's cheating and it's not very scalable. It uses an actual vertex buffer and actual uploads. My final demo is a port of the WebGPU deferred rendering sample written by a colleague on the WebGPU team. I call it the Disco Dragon sample. Yeah. It's a nice demo because it's pretty and it shows off a classic rendering technique for scenes with a large number of dynamic lights. A very exciting disco, I guess. In WebGPU, it's 826 lines of WGSL and JavaScript. In Toucan, it's 495 lines. And of course, it's type safe and all the bindings are by name. So how do we do that? What went away? Well, these are all the objects and constraints that are no longer necessary when you're working in Toucan. So let's get rid of them. Sorry, that was very un-Canadian of me, but it was very satisfying. In the immortal words of Steve Jobs, one more thing. TC, the Toucan compiler, has two backends, LLVM for the host code, and SpearV and Tint for the device code. These, in turn, produce WebAssembly and WGSL, respectively. But those two backends also have other backends. LLVM can produce 32 and 64-bit ARM and assembly, and Tint can produce all of the modern shading languages from SpearV. So from the same single Toucan source file, I can produce a Windows app, a Mac app, a Linux executable, and an Android app, or a web app. So here, again, if the demo gods are kind to me, is that same Disco Dragon sample, maybe the camera can see this, running as a native Android app. So it's 64-bit ARM with Neon SIMD, Vulkan, and SpearV for the shading. Thanks. So in summary, Toucan provides easy access to host-side SIMD, a type-safe and memory-safe API, with less code on more platforms, with iOS to come soon. And in the immortal words of Porky Pig, that's all, folks. This is a link to the GitHub. Feel free to check it out. Thanks very much.
All right, thank you so much, Stephen. I hope all of you check out his project and that all of you become Toucan users. This is it's a great step forward for graphics application development on the latest APIs. Stephen had a backup slide here, which we can peruse later. Now, we're when is our hard stop, Lisi?
5 till.
Okay, 5 till. All right, we have time. I'm going to play the remote presentation from Pawel Misiurski at regular 1x speed as opposed to 1.5x because we have little time. And this is very, very cool. So this is Hop.Earth.
Hi everyone, my name is Pawel Misiurski and I'm working on the project called Hop.Earth, which goal is to allow you to pick any destination on Earth and go for a walk or drive in there. And it's using OpenStreetMaps for the roads and ESRI terrain data for the terrain elevation, as OpenStreetMaps is 2D. So it must be adjusted for the terrain heights, and all kinds of heuristics are needed to allow having tunnels or multi-level intersections. My plan for last winter was to build a road editor using something like pen tool in Photoshop, but in 3D. This is because I needed a new level for my game, which is my browser game called Bad CE, and currently the latest level is basically just flat terrain, and the roads are intersecting at 90 degrees. This is all you can buy from a stock. There are no interesting features, no overpasses or tunnels. And this is why I decided to build a tool to change it. You can buy buildings on stocks because every building is a standalone thing that you can place on any level next to any road, and it doesn't really interact that much with its surroundings, at least not as much as every road. So you can't really buy a road on a stock. So this is why I needed to build a tool that will allow drawing on the terrain, and then came the hard part, which is detecting and building intersections. This is one of the early versions, and all these roads were built using the new pen tool. And here you can see how just dragging from one road to another allows you to create a new road, and these intersections are generated automatically. Generating simple intersections is easy when there are just two roads that are meeting at 90 degrees. So I was not even planning to create really complex intersections. But after adding a few more heuristics and different rules, it turned out that when a few roads meet, it's actually not that difficult to make them create an intersection that makes sense. And this is when I decided to take a look into OpenStreetMap's data and import that into the editor and see what's going to happen. So after doing curve fitting of the center lines of OpenStreetMap's data, it turned out it fits pretty well within this curve-based system. And even quite a few intersections looked not broken as badly as I thought. So that's why I decided to continue with that. And then obviously OpenStreetMap's data is 2D. There is no elevation information on the nodes that create the roads. So to have these roads in 3D, they must be mapped onto the terrain coming from a separate service. So I added a second integration and aligned the roads with the terrain, and created a custom tile server that does it. So it basically combines the two and then smooths the road, because there are some issues with the terrain height map noise, which creates some really unexpected peaks and valleys in the roads. Here's how currently the system works. So in the editor, you can open a map view and then select an area that you want to import. So here we are in the editor and choosing a place to load. You can separately add the terrain or the roads, but obviously we want both. And now you can see how the terrain actually overlaps on the roads, which is not good. That's because the roads were smooth, but the terrain wasn't. So we have to now allow the system to do the second pass. Now, not adapting the roads to the terrain, but now the terrain to the roads. And once it's done, that everything is now clear and nicely aligned. Here on the left, you can see the first screenshot that I took when finally I got the first full screen of not broken intersections, so that was very encouraging. But still, not all intersections, the complex ones, are not correctly generated, not all of them. So the good part is that it's an editor, so you can, after importing, manually adjust this, and over time, with more heuristics, there will be less and less broken intersections. Here is a 5-level interchange, which was generated pretty well, and despite having all these overlapping roads, they are separated pretty well. And now some gameplay. You can see in the lower left corner there is a minimap, which is actually showing you a real map of the world. And this is how you explore the world. And now we will see how a tunnel looks like. So we can see without the holes and with the holes, and they are computed in real time, because the mesh of the terrain is actually not a mesh, it's a height map which creates the terrain in real time, so also the holes must be computed in real time. There are no road or intersections geometries when you're loading the game, so with just a few kilobytes of curves you get hundreds of megabytes of 3D meshes. So once this is workerized or enhanced with compute shaders, then it will allow for having a very fast and seamless experience of exploring the world. Looks like I'm running out of time, so I'll have to skip these performance issues, which are quite common. I will only add that all the roads and intersections are rendered with just one multi-draw call, and they also have LOT. I'm going to skip this one. So yes, currently you must import every level in the editor. So the final goal is that once you're getting closer to the edge of a tile, then the next one will be loaded in the background. So this is still work in progress, and the other one, obviously there are already maps being used as the source, so adding a turn-by-turn navigation sounds like a natural step. I guess, yeah, that will be it for this presentation. It's still work in progress, but you can just go to Hop.Earth and try it yourself, pick up a car and go for a ride. And that's all. Thank you.
So Pawel, wherever you are, thank you so much for putting together an awesome presentation. Everybody, please go to Hop.Earth. And Bad City. I know I've heard this premise before. I can't think of where though. Anyway, so we have a little bit of time for questions. Does anybody have something they'd like to ask? Please go to one of the microphones. Thanks. And all of Pawel's slides are in the slide deck, so please peruse them later.
Check. Hello? Okay.
Yes.
So, yeah, thank you very much for the great presentations and for your awesome work, which is really important, and we are looking forward to WebGPU. I have actually two questions. So the first question, so we have seen in the course on advanced rendering techniques yesterday that hardware ray tracing is becoming pretty ubiquitous in many games. Also, we're seeing work graphs, API on DirectX, and also like with the NVIDIA research address, we saw like the ability to execute shaders, execute neural networks in shaders. So there's a lot of stuff, and we can anticipate that there's going to be some API for that as well. So my first question is, are these on the roadmap or on the radar, and kind of how do you look at these things coming up? And my second question is getting a bit at a deeper or higher level problem, or like a question which is like, it seems like once WebGPU ships, we are probably in a similar space as we are now, where we are basically like 10 years behind the recent advances in graphics. And my hope was actually that we will be at the same level, or we will have only like a 1 year lag or something. So maybe you can talk about that. Yeah,
yeah, sure.
Yeah,
so everything that happens in real-time graphics is kind of on our radar, but the reality is, like, until something becomes multi-vendor, multi-platform, we aren't even really going to consider it very seriously, right? So if you can't use it on, Android, Windows, Linux, Mac, Chrome OS, then we're probably not, gonna bet on it being on it making it to all those platforms until we know that it has. And also, same for vendors. We need significant support from vendors to like expect that it's going to become a multi-vendor standard. So we're not quite as strict there. So we will probably expose a few things that end up being desktop only for a very long time. But at least like we want to see that there's industry-wide adoption, that like we actually think that this is where things are going to go in the long term. So it's pretty tough for us to pick up any things that we can't be confident in. There are a few features here and there where we probably, where there's a lot of demand for them, and we'll probably end up prioritizing those and trying to get those out like as quickly as possible as they start to reach more platforms. But yeah, it's going to remain the case that like we need to wait for the industry to sort of standardize more widely on something before we can decide that this is a thing that we're going to standardize for the web as well. We're going to do all of the work to make it secure. So yeah, it's a trade-off. Things like ray tracing, for example, like we get a lot of requests for it, but and like at this point it's been a few years, and hardware like is catching up. It's starting to be more widely available, but it's still going to be a while, but I think before it is like widely consistent enough that we really are confident in being able to add something to WebGPU.
I have a question regarding, I missed the beginning of the presentation. I was wondering, is there going to be iOS support for WebXR? Was anything mentioned? Right now you have to use a USDZ file.
I'm not aware of any. I don't know. I mean, obviously Apple doesn't pre-announce products, but I'm not aware of anything.
My other question was, in Pawel's, I don't know if I missed it as well, is he using Cesium or is he using like a Google Maps? What's he doing to, what's his data set that he's using?
So his data sets are, the maps are from OpenStreetMap and the terrain is from ESRI, I think.
Yeah, we have like a Google Earth of the human body. My company's Biodigital, and I'd love to be able to do the same thing where you're going from the gross anatomy to, the vessels and seeing it and like riding inside of it. That'd be kind of cool. In a car, that'd be awesome.
That would be an eye-catching demo.
Hi, thank you for these awesome presentations. I was really happy to see that HDR canvas support is being standardized, and I was wondering, because like floating point texture support will be quite important in that case. How are you like planning to deal with like the sometimes lacking floating point texture support on devices like Samsung, like they don't support like linear filtering and stuff like that? Is that expected to be supported? Because I think like the hardware supports it, but it's just
I don't remember exactly what the support level is. I know that Float32 has limited support. So like we have two extensions in WebGPU. One is Float32 blending and one of them is Float32 filtering.
Yeah.
And the reason that they're separate is that ARM has one and Qualcomm has the other, and it's a little silly. But for Float16, support is quite good. I don't remember exactly what all the support is, but we don't have any extensions or anything for that. That's all in core. And float 16 is what we expect to be the target level for doing HDR stuff if you're doing it in floating point.
All right. Yeah, I'm still getting, like on Samsung, I'm still getting fails on linear filtering on float 16.
Yeah,
on Samsung. Same
I
for
don't remember
our
exactly.
RG11B10
Okay.
Formats. But
Yeah, I
so-
don't remember exactly what the level of support is, but please file a bug and say
All right, cool.
you would like to have this feature gap filled, and we will look at it and consider what's available in the ecosystem and try to standardize it.
Awesome. Thank you.
Thank you.
So I'm afraid we're running up against the next BOF scheduled in this room. So why don't we ask more questions outside? I'm sure Kai and Stephen will be happy to stick around. Thank you all once again for coming. This was awesome, and looking forward to see what you build.